Hi everybody. I'd like to start, but there's a cat on my lap, so I need to first turn the music off here. And then I need to move this cat. Maya, you gotta move off my lap. There you go. Go be in your bed. Go be in your bed. No, you cannot come on my lap again. Oh, the joy of cats. She got tangled in a blanket earlier, and now she just wants to sit in my lap and be safe. And I'm like, I have to work. Sorry, pretty kitty. She's just gonna sit there and stare at me. Okay. Hi everybody. Welcome back to Chem 161. We're gonna do Chapter 3 forever. That's basically our lives for the next, I don't know, forever. There aren't any upcoming assignments because you turned in a lab last week. So I even managed to grade it this weekend somehow. The next lab isn't due till next week. Excuse me as I stretch here. The next lab isn't due till next week, so I'm not going to put that on the screen here. And Chapter 3's quiz is going to be due for forever. So, no upcoming assignments. That's nice. So let's just get straight into it. Last week, we left off by assigning quantum numbers to things. And so we defined 3 of the quantum numbers, n, l, and m sub l. And I had you write out all the possible orientations and possibilities for all the different n's and l's and m sub l's and so on and so forth. So you should be able to identify all the rules by now, but just in case you've forgotten. So n is going to be any integer between 1 and infinity. L can be any integer from 0 to n minus 1. And m sub l, we said, was any integer from negative L to positive L. And so these are all integers. So choosing a number for n dictates what values are allowed for L, and then choosing one of those L values dictates what values are available for m sub l. And so they're all connected together. Now, that does mean that there is the potential for some numbers that do not confine or do not conform to those rules. For example, in this right here, if I choose n equals 4, L equals 1 is valid, but for L equals 1, m sub L equals negative 2 is not valid. So be very mindful of that. Make sure that you are not accidentally plotting an invalid orbital. That does not exist. All right, let's talk a little bit more about L today. So L is going to govern the shape of our orbital. To some degree, n and m sub L kick in too, but L tells us specifically what the shape is. For L equals 0, we're going to call that the s orbital. The s orbital is just a sphere. Anywhere inside the sphere is fair game for electrons to be. Remember, electrons are behaving like 3-dimensional waves. So this is a 3-dimensional wave function. And for this 1s orbital, there are no nodes, because there are n minus 1 nodes. Well, n is 1, so 1 minus 1 would be 0. There are no nodes, so the electrons can be anywhere in the sphere. And in reality, the sphere extends infinitely. It's just that the probability of finding an electron infinitely far away from the nucleus is infinitely small. So the odds are very, very, very high. Like, oh my goodness. Sorry. I guess I didn't sleep well enough. The odds are extremely high, like 99.99% or higher, that you're going to find your electron within like 10 to the minus 10 meters of the nucleus. But infinity being what it is, the electron or the cloud technically stretches out to infinity. Now, if I increase the n value, I make a bigger sphere. And that makes sense, right? As you put more electrons around an atom, you need a bigger region to corral them. It would be like putting 2 goats in a small pen and then putting like 8 goats in the small pen. Well, if the pen can only hold 2 goats, you need a bigger pen. So you get a bigger one for your 8 goats, and then another even bigger one for your next 8 goats or whatever. Stop buying goats. You have enough of them. Just like creatures need space to graze and roam and be happy, electrons need space to repel other electrons away from themselves and not get crammed into the center of an atom where they all encounter each other and they all repel each other due to the electrostatic force. But we did say earlier that there are n-1 nodes. So there must be nodes in these orbitals, right? Where are the nodes? Well, they're certainly not angular nodes, because we would see that. They must be radial nodes, which means that at some radius, so if this is my radius, there must be some distance from the radius where there's a node, and electrons are never allowed to be at the node. And so if we slice open the orbital, that's going to look like this. And indeed, in this light space right here, this is our node. I'm trying to darken it a little bit so it's easier to see, but I don't know if I'm helping. Now, what this means is that the electron can never be detected at the node. The probability of finding the electron at the node is 0. Now, to us, that might sound really strange, because how would you get from the inside part to the outside part without crossing through the node, right? In terms of distance. It'd be like walking to my mailbox without actually going through my front door, which is the only way out of my apartment. I would have to like teleport or something. Well, electrons can tunnel through nodes. They're never at the node. They just tunnel through it. That's a more advanced topic that we'll talk about in 360, like 362 or something is when I covered it in college. And it's really freaking weird. Because quantum mechanics, this is where the strangeness of quantum mechanics comes in, is how do my electrons behave like this? Well, they behave like a wave and a particle, right? So it's wrapped up in that. The takeaway that we care about here is you'll never find your electrons at a node. So we could actually draw a probability graph for various orbitals. So I've got 1s, 2s, and 3s here. If you ever see this symbol, psi squared, right here, this is a fancy term for probability. This is basically the wave function that we were using. So I've been saying all along that electrons have a wave function because they are waves, right? Now, we can find out what that function is by doing some crazy-ass math. Let me find this really quickly for you. And you'll see why we're not doing this. It's because it's absolutely ridiculous. There we go. So here are the wave functions for... This is just hydrogen. Yeah. How about no, right? let's get that shit out of here. So yeah, nobody wants this. So we're not going to do any of that math that's involved there. You could do that in 362. But what we care about are the consequences from that math, because we can simplify it a lot. And so if I take that function and I square it, that tells us the probability of where we will find an electron. And you'll see that we are extremely likely to find our electron close to the nucleus. Oh, tablet, why are you like this? We're extremely likely to find our electron close to the nucleus. And the further away you get, the lower the probability is. And it just decays down, 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 down. It never actually reaches 0, but it does decay to 0. The limit as it approaches infinity would be 0. Now for a 2s node, the probability actually does touch 0. It bounces off of the 0 function. Right at where the node is. And then comes back up and then decays. So you're very likely to find your electron close to the nucleus, but you're also likely to find it some distance away. And then for the 3s orbital, again, same thing. So there's a little hump there, there's a little hump after the node, and then there's the peak in the middle. In the middle of the nucleus is what I mean. So left on that graph. So lots of places you're likely to find the electron, but there are nodes that are present, and the probability of finding an electron at a node is 0. So looking at these graphs can help us understand what the shape of the orbital is, because this is plotting R on the bottom of that axis. I should have started with this. R is radius, if you haven't figured that out. For an s orbital, there are always n-1 radial nodes. In other words, at some radius away, you don't find the electron. The probability is 0. What about total radial nodes for any orbital? Then the formula for that is n minus L minus 1. So I'm going to overtype this L with this curly L. So for example, a 2p orbital, a p orbital is L equals 1. N minus L minus 1 would be 2 minus 1 minus 1, or 0. So a 2p orbital would have 0 radial nodes. I think we're doing the p orbital next. Yeah, here we go. Okay. So remember, there are always n minus 1 nodes. And for L equals 1, we must be at least n equals 2. So the first orbital that we would get for p would be the 2p orbital. And we just said that there would be 0 radial nodes for this because n minus L minus 1, or 2 minus 1 minus 1, is 0. But there's still a node somewhere. Where is the node? The node in this is an angular node. And it is the angle around a plane. So I've drawn a shape here. So this is my planar node, and I'm going to just shade over. There we go. So there's one of my planes. Here's another plane. We'll shade that one in too here. And I got the same thing going on over here. So my angular nodes in 2 dimensions, when I showed you the 2D plate with the sand on it the other day, in 3D, those angular nodes become planar nodes. I just saw your question, Chris. Sorry. Yeah, those equations are for hydrogen. There's actually a very minor change that we make for any other element. We just add a z squared term in there, where z is the atomic number, I believe. The real problem with showing those equations is that they really only do work for hydrogen or any other atom as long as there's only one electron. The second you have a two or more electrons, electron-electron repulsion kicks in, and it screws up all your formulas, because now you have a 3-object system where everything is moving relative to each other and exerting forces on everything else, which changes everything's trajectory. And it's basically chaos. So when you get to 361, you're actually only going to study 2 electrons, or 2 body systems with 1 electron. And the common ones are H and the H2 molecule with 1 electron, so H2 plus. Because you just simply cannot make it more complicated and actually solve for the solution. So here's our nodes. We've got planar nodes here, which are our angular nodes. And in these cases here, where I have drawn the planar node, you'll never find an electron on that plane. So that's the node. So for example, in the PZ orbital here, I said PZ. It's my Canadian coming out. In the PZ orbital, you will never find an electron on the XY plane. You can have an XY component, like, so for example, if my electron was right here, it would have XY coordinates along the Z coordinate. It's just that if Z is 0, well, Z can just never be 0. Same thing for PX and PY. Notice that the Z, X, and Y are just whichever orbital direction the balloons, I guess we'll call it, are oriented. So it's the axis. Sorry, that's what I meant to say. Whichever axis the balloons are oriented on. Now, you might remember that for L equals 1, we could have possible values of M sub L would be -1, 0, and +1. And so those are going to correspond to each of these 3 things. And we're going to assign these values arbitrarily. The reason being is that these 3 directions are essentially equivalent. I can orient the z-axis up and down, but I could also have oriented it forward and backward, or left and right, or diagonal like the x and y axes are. And all the other axes will follow suit, because they're all entwined, right? They are all orthogonal to each other, and if you move one, you move them all. Therefore, it's up to us to define where our axes go in space, and the other 2 move relative to that. So therefore, when we assign M sub L values to these, we just put whatever numbers we want. It doesn't matter. All right. And we've already talked about the nodes, so there's our planar node. Now, what if I had a 3p orbital? A 3p orbital would look like this. We'd still have the planar node, but we just have another sort of layer on top of this. And there would be a node somewhere in there. And that node would be a radial node. So I think I actually asked you to draw that orbital on the next page coming up here. All right. The only orbitals whose shapes we're going to really care about are S and P, which makes me sad because I'm a transition metal chemist, so I know like virtually everything there is to know about these d orbitals. Here's just what the shapes look like. And the only thing that I'm going to really write on the slide that's going to matter for this is that for L equals 2, which is the d orbital, M sub L could be -2, -1, 0, 1, or 2. And so that checks out, and that's literally all we care about. You'll notice that this shape looks absolutely stupid. Why the heck did this happen? What do these functions mean? I've got yz, xz, xy, x squared minus y squared, which is like circular? I don't know. And then z squared. Where does this all come from? These are just solutions to the wave function. Or at least common terms that we use to identify these orbitals. And then the f orbital is even crazier. But again, all we really care about for f orbitals, L equals 3, that means m sub L could be -3, -2, -1, 0, 1, 2, or 3. So the takeaway is going to be that for each value of m sub L, we have a specific orientation of our orbital. The numbers for m sub L are arbitrary and do not matter. And the end result is that m sub L is basically a predictor of how many different orbitals you have. So how many places you can put electrons. All right. So I want you, oops, there we go. What I want you to do now is I want you to try and draw these orbitals. I want you to draw 5s and 5p. Try to draw a picture of these. And then answer the questions that I have here. So, how many radial nodes are there? How many planar nodes, etc.? And we'll go over the answers in just a bit. Do the best you can, because it's very difficult to do this accurately, so it's going to look really stupid and sketchy, and that's totally okay. When you're done with that, I'm going to post a link in the chat here. Click on that link, and then just click around and see if what you drew matches what the internet has rendered, we'll say. All right, one more minute, and we'll go over the answer. All right. Now, I'm not going to actually draw these because I'm going to just go to that link that I posted there in case you haven't done that yet. I'm just sort of playing around here. So when I put this on the screen here, you're going to see that I was looking at the 3D orbital. If you're curious, wondering like, where is the planar node on the 3D orbital? It's actually a conical node because of how the math works out. Again, math that we're not going to deal with here. Let's see here. That's as far as I need to go. All right. So what the Orbitron is, let me go back to the previous page here. I was just clicking around on random orbitals here. Is somebody took the wave functions and plotted them into like Maya or Bryce or something that generates 3D models, and he said, okay, render this. I want to put it on the internet for chemistry students. He did this in 2002, so I can only imagine how much rendering time it needed for like computers back then, because computers in 2002 not that great. Turns out, my computer in college not that great. It was good enough, but it was not that great. So you can click on any orbital you want to over here. We were looking at 5s. This is what 5s looks like if you cut it in half. And so you could see that from the outside it just looks like a ball, which is what we want. But each of the different colored sections represents a transition from one node to the other. So there would be a very small intersection here, and then there'd be a node, and then there'd be a slightly bigger section, and then a node, slightly bigger section, then a node, slightly bigger section, then a node, and a slightly bigger section. So there should be 4 nodes in your diagram. And each of those nodes would be represented by lines. And you can see that over here in this diagram too. Each of the different shaded colors. So here's the shaded color, then there's a light, slightly less, slightly darker, we'll say. Darker still, and then darker still. So there are 4 total nodes there. In other words, you should have drawn a giant circle with four smaller circles inside, concentric. Here's what 5p would look like. So the p orbital, let's look at 2p really quickly. So here's what the rendering of a p orbital is. I draw them like bow ties, but people tend to draw them like blobs, like this. So if I do a 5p orbital, the whole thing should look like a blob, but there's going to be like places in it where there are nodes. And so those nodes will look like this. So I should have 1 planar node and 3 spherical nodes for a total of 4 nodes. And if I do this, you can see 1 spherical node, 2 spherical nodes, 3 spherical nodes, and then the planar node is the 4th one. It's hard to see it from here. You can kind of see this here. You can see that there is a yellow inside, so there's 1, 2, 3, 4 regions. Oops, I didn't mean to do that. And each of those regions is separated by a radial node. And then we have our planar node along the XZ axis. This is just PY, 5PY. Oh, no, I have all 3 of them here. Sorry. I looking at the axis right here, like, wait a second, what? I was looking at this one for some reason. Yeah, so the 5, this is PY, this is PZ. PZ, and PX. All right. So playing around with these, you could just see all sorts of different crazy orbitals, and all of their nodes too. And like, I think that I find it just wildly fascinating to look at these. So there's the 4D orbitals. We can click on the 4F orbitals. And like everything gets really stupidly crazy as you continue going on. But you start to see patterns in this stuff. Like, oh, when I go from P to D to F, I'm adding another planar node. And so I'm going to get these like very predictable shapes. And then you can ask yourself the question, are there orbitals past F? Yeah, there's G, H, and I orbitals, and they look just as stupid as you would imagine them to. Now, no elements use these orbitals because they're way too high in energy, and we're going to find out that... Oh, copyright Mark Winter. Thanks, Mark, for providing these, because they're really cool pictures. We're going to find out that the highest orbital that we're really going to care about is like around 7s or so. Once we start associating this with things on the periodic table, which we're actually probably going to do later today, I believe. All right, so that's the Orbitron. I hope you enjoyed that. All right. There's one little last thing to talk about for orbitals, and that is, oh, I guess I can bring the Orbitron back up for this. So you'll notice that the colors on the Orbitron, oops, it just went to phases here. Let me just click on any 2p orbital. You'll notice that it's using like a color scheme where the whole thing isn't one color, but instead is separated into two colors. The reason for this is because the Orbitron is trying to model the phases of an orbital. Because these are three-dimensional equations that are modeled using math, when you solve any equation, such as, say, I don't know, a sine wave here, you have some regions that are positive and others that are negative, right? Those are going to be the phases of the orbitals. The phases really only matter when you try and combine orbitals together. Hint, hint, we probably will do that in Chapter 5 if we have time when we talk about molecular orbital theory, but odds are we're not going to talk about molecular orbital theory until 261. Molecular orbital theory is just, hey, I have orbitals for my electrons around an atom. What if I want to do that for a molecule? Well, you just add them together. And anything with the same phase will sum, and anything with different phases will neutralize. Because a positive number and a negative number will add together to give you a more or less zero result. So phases exist. This is really all you need to know, is that for any orbital, it can be in the positive phase or the negative phase, depending on where the math shakes out from the equations that we have. And it is totally arbitrary. So down here with our n equals 1, this is n equals 1. Everything here is positive. But if I waited for a later instant, I could say, oh, okay, well, everything is negative, right? So it depends. It's arbitrary. I could rotate the whole thing 180 degrees. Now it's negative. Haha. Over here, I have two different phases. And so whenever I have a p orbital that looks like this, one of those is going to be in the positive phase, and one of those is going to be negative. Note that these phases are intended to represent numbers, i.e. math, not charge, which is really unfortunate because what lives in orbitals? Oh, it's electrons. It's really easy to look at this and say, oh, so this is the positively charged part of the phase. No, it is the positive number solution. I actually hate that charge is positive and negative because numbers are positive and negative, and that's super fucking confusing, right? So be really careful. Again, all you need to know about phases is that they exist and they are a solution to the equation. You get a positive number and a negative number, so we have to represent that. It has nothing to do with charge, and we'll probably never talk about it again in 161 or 162 or 163. It's in your textbook, so I thought I'd mention it. Yada 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 phase. Okay, whatever. Wrong button. Hold on. Yeah. Here's the last quantum number. We did not talk about the fourth quantum number. So we had N, L, M sub L. But there's one last quantum number, and it is M sub S. M sub S is called the spin quantum number. Spin is fucking weird. Spin is such a bizarre phenomenon that everything has, and you might think, well, gee, it's just an electron rotating because look at what the picture is showing you. Yeah, this is not actually what's happening. And I actually learned this very recently when somebody linked me a video about quantum mechanics and was like, here's how spin actually works. I can't explain it because it's like 4-dimensional. It's one of those rotate this thing 720 degrees to rotate it once sort of phenomenons. You know, like a USB drive where you flip it around and it doesn't fit. You flip it around and it doesn't fit. You flip it around and it still doesn't fit somehow. And you flip it around a fourth time and it finally works. So it's a 4-dimensional object. Electron spin follows that phenomenon, and if I can find the video, Steve sent it to me. I'm going to have to ask him about it. Someone can ask me, and I'll post it in the Discord after class, but spin is weird. Are USB drives quantum in nature? Not really, because there aren't a quantized number of states that I can turn it. Well, actually, I don't know how I would interpret that. Let's not get too far off track. USB drives are obnoxiously finicky. We can all agree on that. But the end result of the phenomenon of spin is that it causes the formation of a magnetic field. When you have something that is contains an electric charge and it moves or propagates through space, making any sort of motion or twisting or whatever creates a magnetic component. And that magnetic component can go in one of two orientations. It can go spin up, where we arbitrarily assign north as whatever direction we want to call up. And then we can have spin down, which is where the electron orients the other direction. This is all going to be relative to a magnetic field. B is just a magnetic field. In case you've never taken a magnetics class in physics. Third quarter engineering physics, I believe, is going to be magnetism and electric fields. You'll see B there. B is magnetism. I don't know why it's B. And then E is electric field. But when you have a magnetic field in any given orientation, you can either align with the field or against it. Therefore, we need to assign a quantum number for each of those orientations. So we do this. If you're aligned with the field, spin 1/2. If you're aligned against it, spin minus 1/2. So M sub S is equal to either plus or minus 1/2. And that's it. There are only two directions it can align, with our magnetic field or directly against it. So what we're going to do is we're going to take our electrons and give them addresses. Every electron can live in an orbital, and orbitals are dictated by the three quantum numbers, right? N, L, and M sub L. The combination of these three things gives us our orbital, which we're going to put our electron into. Now, interestingly, if I have two electrons that have opposite spins here, like this, electrons normally repel each other, right? And this is due to their electrostatic charges. Electrostatics. Oh my goodness, tablet, why are you like this? Hold on, let me erase these, like, bullshit lines here. Oops, that's the highlighter. That's not what I want. So, electrostatics. There we go. So, because they're both negative, they repel. But electrons are a little bit tsundere, right? Because their magnetic moments cause an attraction. Oh, senpai, notice me. I don't watch anime. I only look at tropes. So I play Persona, so you see a little bit of this and that. But the end result is that in our orbital, we can fit 2 electrons. So in an I can't spell. In an orbital is, I guess, where I was going with this. Oh no. In an orbital, we can pair up to 2 electrons, but only if they have different spins. So you can never put 2 electrons in the same orbital with the same spin, because they would repel. Not only would the electric part repel, the magnetic part would repel too. And so this is called the Pauli exclusion principle. Where is that? There it is, right there. The Pauli exclusion principle is very, very specifically stated. Orbitals cannot have electrons that contain the same spin. Now, there are only 2 spins, so that means at most you can have 2 electrons. But if for some reason we discovered an electron with like a 3rd spin, we might be able to do something with that and then shove it into an orbital, and then we'd have all sorts of crazy shit going on, which would be interesting, right? All right. We now have all of the component parts that we need to start to arrange electrons around an atom, because the ultimate goal is going to be, how do we model this to what we see in the universe? And the answer is, we're going to assign every possible combination of all of our quantum numbers to electrons around the nucleus. Nucleus. I don't know why I had trouble spelling that. And because of the Pauli exclusion principle, we can put 2 things in the same orbital, so the same n, l, and m sub l, but I cannot have the same m sub s. So no 2 sets of quantum numbers can be identical for electrons in an atom. I'm going to have unique combinations of all of my possible quantum numbers for our atom. And so in the next few slides, when is this coming up? It's very soon, right? Yeah, it's literally right here. Okay. In the next few slides, we're going to take all those possible numbers and we're going to turn that into a picture, and then we're never going to touch these quantum numbers again. Which is like, why the hell do we teach you these quantum numbers? Like, we don't really use them in this class, but it's fundamental enough for building the chart that it's not terribly difficult to learn them, I guess. A lot of students hate quantum numbers. Like, it's dumb. And I can't really criticize you for that. But we're going to turn that into a diagram. All right. So for my example here, you have in your notes, hopefully, all of the different orbitals that we determined for n equals 4. So we write out all the possible quantum numbers. So we said, like, okay, so if n equals 4, L could be 0, and for L equals 0, M sub L could be 0. And that was an orbital. And then we did like L equals 1, and you read out all, and so on and so forth, right? How many total electrons can you put in n equals 4? So go find how many total orbitals you had, and then how many electrons are allowed per orbital using the spin quantum number added onto that. Type your answer in the chat, and we'll go over the result in just a second. All right, one more minute. We'll go over the answer. All right, based on your notes or previous lectures, if you don't have the notes handy or whatever, we said that the number of orbitals in a given n would be equal to n squared, right? So for n equals 4, there would be 16 orbitals. Then I could say, well, there are 2 electrons per orbital. So how many electrons would this hold? There'd be 32. Or in other words, it's just whatever n squared is times 2, because each orbital holds 2 electrons. Now, what element holds 32 electrons on the periodic table? It's not going to land somewhere interesting or, like, informative at this point. So if you're looking at the periodic table and you're like, well, wait a second, for n equals 1, 2, and 3, that actually gives me an interesting result. I land on a noble gas. For n equals 4, though, it breaks. We're going to talk a little bit about that and why that happens in the next section. Now, you do the same thing for... sorry, I'm trying to find the eraser here. For n equals 2 and n equals 5, I'll let you do that if you'd like on your own, but I'm going to just go to the break. We've already answered this question. So number of electrons is 2 times n squared. There you go. All right, we are going to take a break. Let me just put the marker right here so that when we come back, that's where we'll start. My timer didn't pop up. There we go. All right, I'm going to start the timer. I'm going to get you some more Fallout music. Hopefully something that sounds a little bit more... Oops, my timer didn't start. Oh, it did start. So hopefully something that sounds a little bit more hopeful. Oh, I know what we'll play. Alright, we're back. I love the music in Fallout. It's just so eerie. Like, the new stuff, I can take it or leave it. But the original Fallout music is just fantastic. Alright, so we're going to do what I said we were going to do before the break, which is we're going to translate all those quantum numbers into a diagram. And that diagram is going to represent the model that we used to display the arrangement of electrons around a nucleus. So here we go. Let's do that. So all of our possible quantum numbers that we can arrange will give us the address of where electrons can possibly be around a nucleus. And they're going to tell us a bunch of different things, such as how much energy they have, what the energy of the orbital is, where the orbital is orientated, and in which orbital the electron lies, that sort of thing. So we're going to put all of that information together into what's called an electron configuration. Now, before we do that, I actually want to draw out the diagram that we're going to be using for electron configuration. So we're going to go over here. And we don't actually need this on the screen, so I'm just going to remove that real quick. Boop. There we go. All right. So what we're going to do is we're going to write out all the possible orbitals, and we're going to just keep doing this. So n equals 1, L equals 0, M sub L equals 0. And when we get over to M sub L, that's going to represent an orbital. And we're going to label our orbital. We're going to draw orbitals as boxes. So we're going to do this for every possible combination of N, L, and M sub L up to 3. We're going to do N equals 3. This is going to be the last one we do. So for N equals 1, I can only have L equals 0. That's the only value that's allowed for L. And if that's the only value that's allowed for L, this is the only value that's allowed for M sub L. So this is all I get for N equals 1, and it's done. Whoop. Well, let me try and draw a straighter line than that. There we go. So now we'll do N equals 2. So if N equals 2, L could be 0. And if L is 0, M sub L could be 0. And that's an orbital. We'll call it 2s. But L could also be 1. And if that's true, M sub L could be -1, 0, or +1. Each of those is going to be an orbital, and we'll call it 2p. And those are all the possibilities for N equals 2. And then what we're going to do is we're going to do N equals 3. And I don't know why this popped up. Hold on. I just have an extra window for my tablet that was there. N equals 3, L could be 0. So M sub L could also be 0. So we got that. We also have L equals 1, where M sub L could be -1, 0, or 1. So again, -1, 0, and 1. Any of those, doesn't matter, it's all arbitrary. And then finally, oops, I got to do my dotted lines here. We could do L equals 2, where M sub L could be -2, -1, 0, 1, or 2. So I got 5 orbitals there, so I'm going to draw 5 boxes. for 3d. So there you go. So now what we're going to do is we're going to look at all the orbitals that we just got, and I'm going to arrange them in order of increasing energy in a new diagram at the bottom of the page here. Well, unfortunately, I've drawn basically everything exactly upside down, because I started at the very top. N equals 1 is the lowest in energy. It's the closest to the nucleus. So let's go down here and we'll draw that. Let's just draw this thing that says... So, see if I can do this right. There we go. Down here, we're going to have the nucleus. And we're going to arrange our orbitals in basically the opposite order that we did them here. So top to bottom. So we're going to take them and just do this bottom to top. So we'll have our 1s orbital. And then we'll have our 2s orbital. And then we'll have our 2p orbitals. 3s. 3p. And 3d. Now, if you have taken this class in high school or whatever, you might notice that I left a kind of a gap right here. There's a reason for that. This is not the complete story, but for now, for the first 3 levels, n equals 1, n equals 2, n equals 3, this is correct. When we get to n equals 4, we're going to find out, oh, something interesting happens. But for now, there we go. We've turned every quantum number address into an orbital. And then once we fill in those orbitals with our electrons... Oh, first I got to do this. So I can start going like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth. I could just start putting electrons into these orbitals. And now, because I was smart and made a copy of this, I could just draw all over it. So this is going to be our template. All right. So this is going to be our what I'm going to call the energy orbital diagram, or the electron orbital diagram, or something like that. The key word is diagram. Because what we're going to do is we're now going to go back and look at elements on the periodic table. For example, hydrogen. Hydrogen only has 1 electron, right? That's obvious enough. Hopefully you have p-table out. Here's p-table if you don't. Oops, it didn't paste. There we go. But if you click on hydrogen, hydrogen only has 1 proton and 1 electron. So what we're going to do is we're going to go over to our diagram here, where I can now turn this back on. So, boop, there it is. And what we're going to say is, okay, I have 1 electron. Here's my electron. That's not a pen. Which I'm going to represent as this sort of curved arrow. The direction of the arrow is going to represent its spin. So this is going to be spin up. And if I draw it like this, that's spin down. Now, electrons will fall. It's like Tetris. They fall to the lowest point that they can, right? So if I drop an electron in here, it's going to fall all the way down to the lowest possible orbital it can go into, which would be right there, right? So I'm going to put my electron right there. There's my electron. Then what I would do is I would say, okay, well, I have 1 electron in the 1s orbital. So I'd write 1s with a superscript 1. And that's the electron configuration for hydrogen. So we're going to use this notation. You're going to write the orbital, and then as a superscript, you are going to write how many electrons are in that orbital. Now, when I'm saying orbital, what I actually mean is subshell, because when I get to 2p right here, for example, I would not write 2p, 2p, 2p over and over and over and over again. What instead I would do is, if this was totally full of electrons, like say this, I would write 2p6. So we're going to write the number in the letter that represents the subshell, and then how many electrons are within that subshell there. All right, let's clear everything off of here. Not our diagram, though, because we're going to reuse that. Let's look at helium. So if I have helium, which has 2 electrons, where in the diagram would the 2 electrons go? I want you to try and fill these electrons into your diagram, because obviously you've written this diagram out, right? You didn't just watch me do this. You're going to want to have it like a giant diagram that you could just use as a model. Like if you have a little whiteboard, draw this diagram on there. Not in Sharpie, because we're going to make slight changes to it in a little bit. But yeah, just fill in the electrons. Where do the first 2 electrons go to make them lowest possible energy? And what would be the electron configuration you'd write for it? Yeah, there you go, 1s2. So let's do that. So I got my 2 electrons. I'm going to put 1 electron right here. And then I can put the second electron in the same orbital as long as its spin is different. So I will do that. And there you go. Now, what do I do? Let's just get a new color here. We'll just keep writing on this. Well, what do I do for lithium, which is 3 electrons? Well, you got the first 2 in there. Where does the third electron go? What would I write for lithium's electron configuration? And how would I draw it on the diagram? Now, importantly, if I only did this, if this is all I wrote, that would make it seem like there's only 1 electron, right? I got to represent all 3 electrons. So I do have to write this part too. So I write it as like an entire sentence. So when we're writing out electron configurations for things, we're going to have this sentence that just gets longer and longer and longer. And then when I write the electron configuration for uranium, you're going to be like, oh, fuck off. Professor West, you're an asshole. I'm not writing the electron configuration for uranium. Guess what? You're going to write the electron configuration for uranium. All right. But importantly, you could see how this is going to start building in our diagram. Oops, I didn't actually put the electron in here. So there we go. And like as we start putting in more and more electrons, we're going to fill orbitals, and we're going to progress up through the diagram. Now, if I go over here, we might notice something that's fascinating, provided that my web browser can find it. Well, there it is. It's like 7 things down. Boop. All right. If we look at p-table here, I don't have all of my elements shown. You know what we can do? We can just do this, because this is the important part that I care about. All right. Notice that for the first 3 elements, I filled the entire n equals 1 level after helium. So once I put in 2 electrons, all of n equals 1 was full, and I had to go to n equals 2, which incidentally is the second row of the periodic table. What do you think happens when I do neon? Let's do neon's electron configuration real quick. So neon has 10 electrons. Let's get a new color out for neon, though. Green, sure. So neon, which has 10 electrons. Where would I put all 10 electrons? Well, I'd do something like this, right? 4, 5, 6, 7, 8, 9, 10. And so that would be 1s2, 2s2, 2p6. And if I wanted to do sodium, which is the next element, I got to go up to n equals 3. And look at that on our periodic table. There might be a pattern here. There's totally a pattern. What do the rows mean? The rows on the periodic table correlate to n. That's why the periodic table is built how it is. Isn't that cool? So every time you go to a new n, you go to a new row on the periodic table. So your s orbital, 3s, 4s, 5s, 6s, whatever, is always just going to start on the left-hand side there. So from whatever previous row I go to, when I go to the next one, that's the start of n equals 5. So 5s is always going to be these guys over here. Do I have something that actually says that on here? Sorry, I'm just going to click around for a second. Doesn't say orbitals in here. That's too bad. Okay. So we'll come back to that. So let's go back to my slides here. And so we can write our, oops, I got to click on the thing here before it'll do anything. So we've already done this for hydrogen. There's our arrangement of the terms and what we write. We did helium. We put it in a picture. There we go. I'm trying to get to an example. Like we've talked about all this. Oh, is there an electron tab up at the top here? I didn't know that. Oh, look at that. Yeah, that's exactly what I was looking for. There you go. That is not the... That's the Orbitron. That's not what I want. That's what I want. Yeah, there you go. So you're going to see here, you could click on any element now, and you could see there's the electron configuration that it's going to go. Now, it's going to show you all sorts of crazy stuff, and it's probably going to show you exceptions. Like, I think niobium is an exception. I don't know. Where's my exception here? Yeah, there's an exception right here. That one we can predict, though. What about down here? Okay, yeah, some of these are strange exceptions. That's what I want to. We're going to follow some basic rules here. I don't want you to just go to p-table and be like, oh, here's the electron configuration, and copy it out of here. We're going to be able to predict certain configurations that I will expect you to know, and then there will be others that I won't expect you to know, and just fill it out by filling it in normally. But this is what I'm talking about. This is the electron diagram up here. And you can see that these d and f orbitals don't really line up where we would expect them to. And we're going to get to that. So we're going to just stick with elements that are down here. I got to actually click on it before it does that. But yeah, play around with that and looking around it and see what you can find that is interesting, because that's how we're going to relate. That's how we are going to relate all of the quantum numbers to electronic structure. We're going to represent it as that diagram. Now, you saw on that diagram, and also when we drew it, that when I ordered the energy levels, I put 2s below 2p. I put 3s below 3p, below 3d, and so on and so forth. There's a reason for this, and the reason has to do with how many angular / planar nodes are present. Higher angular momentum numbers will have more energy, which makes sense, right? Something that has a higher momentum would have higher energy associated with it. So we're going to arrange that very slightly higher on our diagram. So, for instance, when I put n equals 2, I will always put 2s below 2p. When I put n equals 3, I will always put 3s below 3p, and that'll be below 3d. Now, there could be other shit between those levels. And in fact, as we get later on, we're going to see that the levels sort of blend together in a really odd manner. But this will always be true. Within a sublevel, S will be below P, which will be below D. So as long as all of these numbers are the same, this will always be true. And then N can be whatever number you want to. Although, if I have a number less than 4, some of these orbitals don't exist. For example, 2F doesn't exist. There's no 2D. There's no 1P. Those don't exist. So just be careful about that. What does N equal 2 look like? We've already done that. All right. One term that I do want to make sure that you know is the term degenerate. Any orbitals that have the same energy are degenerate. What that means is that they are indistinguishable from each other. Their orientation in space is arbitrary and is up to the viewer. Just like if I draw a coordinate axis, I believe this is the standard notation. Actually, X and Y might be swapped. I don't know. I know Z is always up, though. Or you could draw it, in any orientation you want to. Like, maybe you really want to piss somebody off who's a physicist. So you put Z over here or something like that. And we'll say, okay, we'll put X on the top. X never gets to be on top. Equal opportunity variables, man. That just looks really foreign to me, putting X up there. Like, that's confusing. But the point is, you could do that however you want to, because you could just orient them in space in any direction you want. So, when something is degenerate, it means it has that level of symmetry. In terms of its energy, all of those orbitals will be equivalent. So, that's going to be relevant for as we add in electrons to things. So, let's start doing that. We're going to put oxygen and electrons in. So what I want you to do is first write down the electron configuration statement or sentence for it in the chat here. And then we're going to try and fill in the electrons in the diagram one at a time. And we're going to see if we get any extra information from drawing the picture versus drawing the sentence. So write out your electron configuration statement. So 1s2, etc. All right, let's write down what you should have gotten. So if oxygen has 8 electrons, so I'd write 1s2, 2s2, so that'd be the first 4, and 2p4, which would be the last 4. So now we got to fill in those 8 electrons. So here's my first one, and here's my second one. That's easy enough. And then, bam, bam. But then I get to this point, and I say, okay, well, what's the next logical step to do? Because you could pair an electron, but electrons do repel, right? Which would be less energy, having 2 electrons repel, or, because all these orbitals are degenerate, putting it in the next spot. And the answer is, if the orbitals are degenerate, do 1 electron per degenerate orbital. degenerate orbital before pairing. So that means that the 6th electron would actually go here. And the 7th electron would go here. And the 8th electron, well, there are no more unpaired orbitals. So we'll start pairing them down. You can think of this as, hey, we have 3 apartments available. One has somebody living in it already. You're going to pay the same amount of rent regardless of where you live. Would you rather live with a roommate or live with yourself or live by yourself? And electrons always opt to live by themselves rather than live with a roommate. Unless there are no other options available. Then they pair up. And so this is called Hund's rule. Hund's rule says if you have degenerate orbitals, put an electron in every degenerate orbital before you pair them. That's because the energy that you get back by pairing opposite spin electrons is not as much as you would get back by not having the electrons pair in the first place. Electrons pairing with opposite spins is like an optimization. It's not great, but since we're forced to do it, we can. And there's our electron configuration. All right. So now what I want to do is I want to give you a bunch of these, and I want you to... Oops, that's not what I want to do. I want you to play with your electron configuration diagram or p-table and click around. And then write out the electron configurations 1s2, 2s2, etc. Blah, 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 blah. Go ahead and do that, and I'll check in about 5 or 6 minutes. You can type your answers in the chat as you get them. All right, one more minute. We'll go over the answers here. All right, so let's write these out. I'm going to write out their electron configurations first here on this page. Oops, I got to turn this down. It's too hot in here. So for fluorine, we would have 1s2, 2s2, 2p. So 4 plus 5 is 9. So that would be fluorine. And then for phosphorus, I would have 1s2, 2s2, 2p6, 3s2, 3p. Let's see here. 6, 8, 10, 12. I need 3 more. Basically, when you're checking these, when you sum all of these numbers together, you should get the total electron count, right? So that's a good check. Just to be sure that, hey, you've done this right, because you should have the same number of electrons. That's a button that I meant to hit. Womp womp. Can I undo that? No, I can't. Okay. Well, thankfully, it's saved on the internet forever, so you could pause the video and rewind. I, unfortunately, cannot do that. All right. Anyway, there's argon's electron configuration. And now we can go over to our diagram, which I've saved here. Whoop. Oh no, it's full of crap. Let's just erase it all. There we go. And so we will fill in our electron configurations for each of these. So, we'll just go over here and do that. So for fluorine, the diagram would have 9 electrons. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, whichever one has your unpaired in it, actually, let's zoom this in a little bit. Whichever one has your unpaired in it doesn't matter. Convention is to just go left to right, but they're all degenerate orbitals in the 2p subshell, so we don't really care. I'm just going to work left to right because that's what I've done. So there's fluorine. Phosphorus has 15 electrons, so we need to go 10, 11, 12, 13, 14, 15. That would be phosphorus. And then argon has 18 electrons, so we'll go 16, 17, 18. And that's what argon's electron diagram would look like. Now, you might think that the next atom should put its electron in 3D, but if you look at the next atom on the periodic table, the next atom after argon is potassium, and it's in row 4, which means that something strange is going to happen. And that's this. This is going to happen. Why the hell does that happen? That's a problem for future you, as in on Thursday. That's all I'm going to do. I realize we have like 14 minutes left of class, but the next topic is involved enough that it will take more than 14 minutes. So, you know what? Good enough place to stop as any. So, thanks for coming out to the lecture. We'll end a little early today. We are dealing with very difficult topics, so make sure you are asking me questions in the chat or the Discord or email or whatever. I'll be around today to answer them if you have them. That's all I got from me. There's no upcoming assignments, so, study some quantum mechanics, go look at your exam results, and go out and enjoy the sun. It looks like it's a nice day out there. Take care.